give people a 2-minute. Start in a couple of minutes. We'll give people the usual 2-minute academic leeway because they'll all be strolling in after a long night of work probably. They'll all be coming in soon. So we'll start in 2 minutes. So if you want a little bit more coffee or juice, now's the time to. Okay, it's 2 minutes past 9, so time to get started. Good morning, everyone. I'm happy to welcome you all on behalf of my co-organizers, Jan Trmal, who's sitting over there, and Najim, Dehak, and Philip Kuhn, who's upstairs. This is the culmination of 2 months of very intense, tremendous work by a large group of people, which was preceded by even a lot more work over the spring. And this is essentially the closing presentations of the 5th Fred Jelinek Memorial Summer Workshop on Speech and Language Technology, or JSOLT. Let me sort of start by quickly reminding you how we got here. So we call it the Summer Workshop, but the work for putting it together actually goes on all year round, as I've surely told you once or twice before. We started this whole exercise back in September. We typically do this every year that way, where we call for ideas for what to do in the summer. In October, we typically ask people to write down just a page or two of what they think the projects could be about. In November or so, we have a meeting where we bring in the project proposers and other experts and brainstorm and try to figure out what the best projects are, select 2, 3, or 4 to work on in the summer. We have to raise money, we have to get team members. You'll be surprised how, maybe you remember this, that in the beginning, it sounds like, oh my God, 2 months is such a long time to commit to be away from home, working somewhere else. Of course, once you're here, 2 months go in the blink of an eye. But back in November, December, we have to persuade people that it's worth their time to come here. Some are easily persuaded, others not so much. And then eventually we put our teams together, we get the grad students, the undergrads. And there's a lot of planning that happens in the spring. Typically, each team meets at least once, more often than not twice, face-to-face for a day or two, trying to figure out what we're going to do in the summer. And then finally, when we get here, the work actually starts in June and July. So for this year's workshop, the call for proposals went out in September. This is like the top half of it. I don't expect you to read this, don't try to. This just says that, hey, we're looking for good ideas, and if you have a good idea about what to do in the summer, write it down on a piece of paper, send it to us. We're looking for ideas in speech technology, NLP, multimodal interactions with machines, dialogue, language and healthcare. And we sort of put this out. But of course, just putting out a shingle and hoping that people will reply to you isn't always the best strategy. So typically we harass people. We send direct mail to several thousand people who are our friends and associates from over the years. We typically call people and say, hey, at the last conference you gave this paper. That's a great idea. Can we put a team together around that? Or, oh, you two guys are doing something together. What if we had another 3 people and 5 students? Wouldn't that be great? Come propose something. So we sort of try to cajole people who have ideas to think about it. And we did that too this time. We got 12 proposals. Of course, some proposals are just not the right kind of thing for summer, so each proposal gets read by a couple of people, and then things that are a complete no-go, we sort of politely turn them down in the beginning, and then the rest we invite. So this year we had the planning meeting or the discussion meeting for the proposals back in November 10, 11, 12. This meeting is run in this interesting way where it's a peer review meeting like you do for proposals or things like that, except it's interactive. So the people proposing and the people evaluating are all in one room discussing, debating, brainstorming, trying to figure out if the proposal can be made better and so on. And so there are both the proposers and others. And of course, we have a very elaborate way of trying to figure out what the sentiment of the room is. We use this crazy single transferable voting system that Jason Eisner can give you a whole 2-hour lecture on, and so on. And for this year, the meeting had a nice representation. About 55% of the people in the meeting were academics, another 25 were industry. So we have a lot of industry participation in these workshops, which is very encouraging and healthy because it means that we are working on problems that will really have impact on the world. We have a few government representatives who sort of come in. Sometimes they're able to bring some government support. And more importantly, the US government otherwise funds a lot of research, so they find this discussion very interesting to see where the field thinks it wants to go. And of course, there are some outcomes organizers to moderate and run the meeting. So this is what we had this year, about 11 authors, 13 non-author experts, 5 faculty, and then we had representatives from Amazon, government, Facebook, Google, Microsoft, Mitsubishi, and it was a pretty intense meeting. So at the end of the meeting in November, we selected 3 teams and they got working right away to prepare for the summer. So the first team we had was titled Grounded Sequence-to-Sequence Transduction. This team is led by Lucia Specia, who's sitting back there from Sheffield, although I'm told she's soon going to be at Imperial College in London. And it has 5 other senior members, 6 graduate students, 3 undergraduates, another 3 people who are affiliated with the team. This includes people like Christian back there, who worked really hard to get the team together, put the data together for it, but actually couldn't come for the workshop itself for various technical reasons. So he counts in that 3A, that's why it's grayed out a little bit, but there's a lot of effort of people behind it. This team had 2 meetings, once early on at Facebook in New York and once later on in Pittsburgh at CMU. Again, these are 2-day meetings with a lot of discussion, trying to really crystallize what they're doing for the summer. The second team is General Purpose Sentence Representation Learning. This team is led by Sam Bowman, who is over there. And Sam and Ellie, they also had a nice team. There's 5, 6 senior people in that team, 6 graduate students, 3 undergrads, and again, a number of people like Western from Facebook and Panjan Das from Google, people who came in for a few days here and there, but were working behind the scenes to make things happen. And again, this team also had an intense planning meeting, once in New York and once again in Baltimore. And then finally, the third team worked on multilingual end-to-end speech recognition from incomplete data. The focus here is how to build speech recognition systems when you don't have a lot of transcribed speech, whether you can use speech only and text only. This team is led by Takaaki Hori from Mitsubishi Electric Research Lab, who's sitting over here. And that has 3 senior people, 5 PhD students. And this team was a little bit different from the others. There's a 10P. So there are a lot of people, 10 different people came here for 5 days, 3 days, 8 days. It was like my head went dizzy. Every time I went into the lab, there were 3 new people over there that I hadn't seen the previous week. And so it was quite a fun team. And this team also had they got a slightly late start, but they also had a planning meeting in May. And so these are the 3 teams that you're going to hear from today. Right? So if you look at what kind of people came to the workshop, this was my demographic slide at the beginning of the workshop. It's still mostly true statistically, but if you are paying attention, I list here 34 full-time and 14 part-time participants. If you add up the numbers in the previous slide, it's more like 40 full-time researchers and 18 part-time. And this is really amazing that once the workshop started, people said, hey, this is too good to miss, I'm going to be there. And we just kept saying yes and yes and yes, and so we really had a nice group of people. But just to sort of give you a sense of how the workshop groups normally look, we're doing okay, not so great. We have about 75% men, 25% women. We have about half and half between senior members and students. If you look at the senior members, there's a nice balance. It's about 60% from academia, 40% from industry, which is great to see. Among the students, it's about 3/4 PhD students and 1/4 undergraduates. In terms of institutions, this is a great thing. I always like this. There are 22 different institutions, 14 from the US, 8 from outside the US. And these include both academic institutions and industries. So if you look at the countries, they're from the Czech Republic, France, Japan, Portugal, Spain, UK, and of course the US. And so if you think about it, we have about 45 or maybe 50 people from 22 different institutions, which means it's not like one institution dominates who comes here. It's really spread out over many, many places. And of course, a lot of these workshop activities, the housing and everything requires money, and so we've had a nice diversity of sponsors. Google has been supporting us since 2008, but over time, more and more people have joined. I'm very happy about it. So Amazon, Facebook, Microsoft, Mitsubishi, and this year we have a new sponsor who's joining us, which is Immortal. Thanks for that. And so this is what the workshop themes were. So what did we do in these 8 weeks? So here's sort of the workshop calendar. We started on June 11, and we are now on August 2nd. So the first couple of weeks was training camp or boot camp. So we had all the students attending a summer school while they were also preparing their team's research and setting up lab things and so on. And these were typically a couple of lectures in the morning, a lab in the afternoon. So this is pretty intense training. I've added up the number of contact hours we have when we do this. If you add up the lecture and lab times, it's the equivalent of 1.5 semesters worth of contact hours with instructors. So in 2 weeks, you get you get a brain dump of all the HLT knowledge that is out there. This had a class on deep learning, computer vision, in speech recognition, machine translation, natural language processing, information extraction, the works. And so this was an intense 2 weeks. Then we started our formal part of the workshop, the researchy part, where the senior people show up on June 25th. And from there, it was like a big sprint. So what all did we do? Well, we did a number of things in those 6 weeks. One of the fun things we do is every Wednesday, Jason Eisner, who just entered the room, back there, and Paula Garcia, who's over here, and a couple of other faculty members, Najim, we met with the undergraduates over a brown bag lunch. And by the way, when I first started, I didn't know why the brown bag, but then I realized when you bring your own lunch, you typically bring it in a brown bag. That's why it's called a brown bag lunch. So we sit and sort of talk to the junior-most people in the workshop and try to make sure they're on track, that they're enthusiastic about what they're doing. We, of course, do other fun stuff. So we have social outings. So everybody in the workshop got to taste some of the more fun food in Baltimore. So these are typically outings to local restaurants, including one owned by the father of Hamid Karzai, and so on and so forth. But what is more fun is that we had all these plenary lectures. So we have really smart people. So Deborah Matthews came by on June 29th. She's at the Hopkins Bioethics Institute, but she was talking to us about more generally about ethics and morality and principles in AI. How does one think about AI in a way that's ethical and right and so on. We had René Vidal give us a very nice lecture on the basic mathematics of deep learning. Like, why do these deep learning algorithms work the way they do? There are not many theorems known in this field, and René has some of the more interesting ones, which, for example, tell you that under some very fairly mild conditions, these deep neural nets have the property that they have lots and lots of local minima, which are all global minima. So that's why some of these algorithms they use end up working as well as they do. We had Brian Roth come in and give us a talk about input methods. So if you think about it, we are used to the usual QWERTY keyboard and so on and so forth. Most of us are, but there are all these languages in the world, and you might start thinking, how do people enter text in these other languages? So Brian has been looking at it as a very generic problem, and he works with the Gboard team in Google. So he talked about how text input can be thought of as a language modeling problem, and it's a technique that sort of makes you think multilingually when you think about HLT. We had Kyung-Hyun Cho from NYU. He's another deep learning person. He came and talked about some of his ideas in sequence-to-sequence transduction, particularly applied to machine translation. And then we had Yulia Svetkov from CMU, and she came and talked to us about language generation. Can you generate language which has a certain style, a certain flavor? And this is very important in human-computer interactions because you want your computer to behave appropriately and produce language that is appropriate for the situation. So she has some nice papers in this area. So all these were sort of the other intellectual activities and social things that happened. And this year, after many, many years, 4th of July happened to be in the middle of the workshop, and instead of just telling everybody to go to Washington, DC to see the fireworks, we had a pool party at Najim's house. And this is a picture from the pool party. So yes, we worked really hard, but we also had a good time. And that's what has brought us to where we are today. So this is the agenda for the day. I will hand off right away to Takaaki Hori. His team will give a presentation through till the end of lunch, to the beginning of lunch. Lunch, we are on our own. When we come back from lunch, Lucia's team will talk about the sequence-to-sequence grounded transduction models. And then at the end of the day, we'll take a break. And tomorrow morning, we'll have Sam and his team present about sentence representation learning. So Takaaki, may I give it to you? Setting up, let me just say that we are going to all thank our sponsors formally at the end of the program tomorrow. So today I'll just show you this brief picture and move on.
Good morning. My name is Takaaki Hori. I'm a team leader of this project with Shinji Watanabe. And we have two senior researchers, Martin and Ramon. So first of all, I'd like to introduce our research project. And after that, I will present a brief summary of our accomplishments in this workshop. And after that, so each research topic will be presented by corresponding team members. So, okay, so I'd like to start the overview of our research project, multilingual end-to-end speech recognition for incomplete data. So yeah, now speech recognition technologies are widely used in the world. But basically the LSR system is language dependent. So it's very expensive and time consuming to build an LSR system for a new language. So this is a big problem. And actually, it's not impossible to increase supported languages like Google, right? So if we can spend much money and make big effort to do that, but usually it's not easy. So this is good. So yeah, increasing the supported language is a good thing. But however, there are almost 7,000 languages in the world. So the question is, so how do we support more and more languages? So the goal of our project is to answer this question. So to tackle with this big problem, we worked on two research directions. First one is multilingual end-to-end speech recognition, where we want to reduce the need for expert knowledge when building an SR system for a new language. So where we investigated new model architecture and algorithms to improve the end-to-end SR for multiple languages. And the other direction is to develop learning algorithms for incomplete data, where we want to reduce the cost for collecting complete data, i.e. Paired speech and transcription data. And where we investigated new algorithms for training end-to-end ASR models with incomplete data. So we considered different incomplete data scenarios depending on the amount of complete data for a target language. For some languages, we already have moderate size training data, but in some other languages, we only have so 50 hours of training data or less amount of training data, and in some languages, we don't have training data, so it depends on the amount of training data, and we can consider different scenarios, so zero resource, low resource, moderate size resources. And in this project, so we assume we can use incomplete data, such as paired data, so training data from other languages, and also we could have unpaired data in the target language. And also, so if possible, we can use some extra knowledge, like phonetic information, but it's very limited and not complete data. And so usually, as you can see, so depending on the amount of complete training data, the error rate will change, like this curve. And in this project, so we want to reduce the error rate in all the scenarios like this. So this is our objective in this research project. And so we worked on in this all the scenarios. For example, so in the moderate size resources, we investigated new architecture and training methods. For low resource scenarios, we worked on the multilingual training and adaptation techniques. And for zero resource case, we investigated running algorithm for unpaired data. And in the case of using extra knowledge, so we worked on some use of auxiliary data situation. Okay, so please.
So then we also want to summarize the major accomplishments during the workshop. And we have actually two parts. And one part is this slide. First, build a multilingual end-to-end SR system for 17 languages. And also that we had a significant improvement with the novel architecture and the training. This is done during the workshop, so that we actually submit already 3 papers to SLT during the workshop, and we will have more in next coming conferences. And summarizing the several the notable achievements, for example, the first one is multilingual SR and adaptation. We actually successfully built the adaptation techniques for the Babel data, and getting the number is a hybrid ASR conventional system 49%, and our end-to-end system is 51%. It's very comparable. It's usually in this range of the data, end-to-end system doesn't outperform the speech recognition the conventional system, but we are crossing to the conventional system by using the end-to-end system. This is a great achievement in this community. And also the decoding, design, and language modeling, we are achieving the best Wall Street Journal water rate in the end-to-end speech recognition system. And we actually already have a 5.6. It is the best record in the end-to-end system. It's also the improved further from 5.1% by using a the language modeling in the decoding. We also, with the help of the Google, start to investigate the minimum word error rate training, and which, again, the help of the Google, we got the 8% reduction rate for the libre speech task. And during that, we also implement the GPU-based parallel decoding for the end-to-end system. And the other is multi-encoder architecture. We basically have several architecture in the encoder to get quite a nice improvement for the end-to-end systems. And the second one is more like a very challenging and have a scientific the aspect. We try to build end-to-end ASR TTS chain and unpaired data training. So the first one is a back translation style ASR training. We actually built a TTS, the text-to-speech, but modified it to the text-to-encoder state, and got that 12% relative improvement with the data augmentation techniques. And given that, we also started to implement multi-speaker, multilingual TTS for the data augmentation purpose. And the other one is the cycle consistency training. We try to jointly train ASR and TTS in an end-to-end manner, which also have a still investigation stage, but we have some promising results. And the other one is variational autoencoder. Same the motivation. We try to model ASR and TTS in one framework. And the third was the multimodal data augmentation, which is more like the approximation of this cycle by using a phonetic information. And this actually we got several nice improvements from the baseline. And through this kind of the achievement, we put all the kind of techniques together in one open source framework, ESPNet. And it's actually developed for this workshop and getting more popular and popular. During the workshop, GitHub star was increased from the 200 to 330 already. And that has a quite nice function in terms of having an ASR and TTS, both recipes, in the speech processing toolkit. And this also follow the Cowdy style so that we can easily port a lot of the Cowdy outcomes to this end-to-end system. So this is a kind of major accomplishment of our team. And now we move to the individual presentation. First done by the multi-encoder by the Harish and Rizzi. Yeah. Could use the somewhere.
Hi everyone, my name is Riji. I'm a Hopkins student, and me and Harish are going to present our work in this workshop. This work is done with JJ, Adi, Shinji, Nelson, Martin, Karthik, and Takaaki. So this is the topic that the whole project, the big picture of our workshop. So our sub-team is focusing on the moderate size resources. We're trying to explore new architectures to reduce the error rate. And focus of our sub-team. We want to improve the end-to-end architecture so other aspects of our topic can be improved by the improvement of baseline. And also we explore the multi-encoder approach, which gives us a quite nice game. We use several encoders to capture diverse information. Optimal fusion of these encoders will hopefully improve overall performance. And then we also explore alternative architectures for encoders, different from the default BISDN encoders. We explore these convolutional-based encoders for end-to-end system. Before we go into the more detail, I will just start with the database so we can see the results step by step. I started with the Vietnamese language from the Bubble project. Vietnamese, the data type is manually transcribed conversational telephone speech with 79 hours for the training set. Development set has 9 hours, evaluation set has 11 hours. And we used 80-dimension FBank features plus 3-dimension speech features. And the results that I'm going to report is going to be in character error rate. So this is our baseline architecture with BRSDM. P stands for prediction. So we started with the joint CTC attention model. The input feature is fed into the encoder, which will provide the encoder states, and then the encoder states will be fed into a CTC model and then the attention mechanism. Those CTC and attention mechanism will jointly make the prediction. And on the right side of the picture is our encoder architecture that we started from, which is 4 layers of BRSDM with projection. And also it has subsampling factor 4. So if input feature is 100 frames, our output is going to be 25 frames. 25 frames of encoder states. Previous study has also have already shown that adding VGG layers in the encoder will help the speech recognition. So we follow this direction. We add the initial layers of VGG net architecture, and there are 2 max pooling layers in the architecture, followed by BRSDM layers. Here's the results that we got. We got some almost 5% absolute improvement, just putting VGG layers on top of this. And this is our proposed multi-encoder architecture. And instead of 1 encoder, we use like 2 or even more encoders in this architecture, so that our intuition is every encoder, every different architecture or features will carry diverse information. And then with this hierarchical attention mechanism, hopefully we can fuse the information from each stream to get the better results. And each encoder, encoder 1 is the VGG BRSDM that we just saw, and encoder 2 we use the BRSDMP. In order to make these 2 encoder diverse, the VGG BRSDMP does not have subsampling. And the attention mechanism is the content-based attention. And here's the hierarchical attention model. For each encoder, we have a attention mechanism for each encoder, and then we have stream attention to select which stream we should put more attention to. And this is the function. And then beta 1 and beta 2 is actually learned by the attention mechanism. And this framework is also suitable for encoder with different frame rate. And this is the results that we got. Without any CTC, we just use pure attention model. We get quite a nice game, like relatively 7.2 improvement. And also we want to add CTC in this model. First, we add CTC is we add CTC objective as a constraint technique, so that CTC will encourage the monotonic alignment. With the shared CTC, we also get even better improvement, relatively 7.4 compared to the 40.4. And in this case, shared CTC, shared CTC will perform like putting the same constraint, putting the same constraint to the both streams, which is not what we really want. We want to each stream perform differently, so we add a different CTC for each stream. We get even better results. So we get 34.7, which is another relatively 7.2 improvement. And further, we add language modeling in this architecture. RNN language modeling, we get small gain, relatively 1%. And here's some analysis of the subsampling rate.
Question? On the previous slide?
Okay.
What does it mean that there are 3 arrows pointing into the top? How do you combine the result?
Yeah, so the decoding results, decoding scores is combined from CTC and attention and then the RNN language model.
So you're saying that this is like a product of experts model on the words on the output word stream?
It is during the decoding, beam search. So it's not exactly, but it's anyway combined the scores during the beam search for all of
Okay, you just add or multiply the scores.
Exactly.
Just add, yeah. And
Actually,
here,
before you go on, I had another question. Just go back to the slide. So when Shinji was giving the highlights, he was talking about the Vietnamese system, and he said the overall error rates are in the 49-51% error rate, but those are word error rates.
those are word error rates.
And these are character error rates, and I'm trying to reconcile the two. So do you have a rough sense of if I had a 40% character error rate, what's the corresponding word error rate, and vice versa?
Yeah, 40%, usually like 15 or 20 more,
Okay,
depends.
so this would be like a 60% word error rate system.
Ish.
Okay,
Yeah,
and
in
so
the
at this
beginning.
point, this is not your best system, if you will, because he said eventually you got it down.
Well,
to 50.
34 is actually 49.
So that's the one that Shinji
Yeah, yeah,
mentioned.
yeah.
Okay, all right, just making sure. Okay.
So we
30
started from the very beginning, and
Right.
then we reached to the bottom line, which is the best model that we have.
Okay, so your starting point, 44% to 43.7 character rate is about 60 something, maybe 65%
Yeah.
word error rate. And then by making all these, whatever, I guess, design changes and some training changes, you're down to 51% error. Okay.
Yeah.
You get the RN, sorry, that gives you character.
Gives character, yeah.
Rate improvements.
Yes. Okay. Thanks for the question. And so two stream with same sample subsampling factor and different subsampling factor actually plays a very important role here. Different subsampling rate actually gives like relatively an absolute 3% improvement. So which proves our points that different stream carry different information will help this framework. So this is the overall results. If there's no CTC, only a pure attention model, we started from the BSTMP with subsampling, and then without subsampling, and then we have VGG, and then using our framework, we got from 43 to 40. And then with CTC, we got from 43 to 34.4. And so Harish will present some our observations on the CNN encoders.
Hello everyone, my name is Harish. I'll follow Hari's presentation on new architectures for end-to-end ASR. So as Ruji already showed, having different types of encoders is beneficial for the multi-encoder system and overall end-to-end ASR's performance. I explored a few alternatives to the default VLSTM based architectures. So I mainly focused on the non-recurrent architectures, and it's mainly on the CNN variant of the encoder. So I don't have any positive results like Lucia had, so this is still like a work in progress kind of slide. And also the numbers are on a different data sets, that's why we see much lower numbers than what Lucia showed. This is on Libri speech clean test set. So with the baseline VLSTM based end-to-end ASR, we are getting something around 7.2% character rate. We experimented with 2-3 variants of CNN based architecture. The second row is a purely CNN based encoder without any recurrent component in the encoder. So we see a significant degradation in the performance, the word rate tripling. And then we experimented with we added dilation to the CNN, which gives us much better context as we go along the depth of the network. This seems to be important and is providing us nice improvements. And just out of curiosity, what I experimented with adding just one BLSTM layer on top of the CNN with dilation, and that seems to bring down error rate significantly. So we are still experimenting with other variants of the CNN, and hopefully we'll get on par with BLSTM and hopefully beat BLSTM-based system. So
may I ask you a question?
Yes.
So I guess one difference between the BLSTM and CNN is the recurrent structure, but the other one is the bidirectionality. So in the
yes.
BLSTM, you're getting information from the backward pass.
Yes.
So in the CNN,
so we are looking at so CNN has a kernel, right? So
Right.
we are looking at frames, past frames and the future frames.
right, but still it's finite, right?
It's finite.
It's probably what, 10, 15 frames,
Yes.
30 frames maybe.
Yeah.
Do you know what is the bigger cause of the difference? Is it the fact that it's not
I think,
recurrent, or
I
is it
think
the
the-
fact that it's not?
I think the context, it's, CNN is able to see only finite context.
Okay.
If we kind of increase the context by adding more layers or use dilation like much more aggressively, you can get a much bigger context. So my intuition is we don't need a very
Fully recurrent.
fully recurrent architecture for encoder, because we anyway have attention which kind of take care of the.
Okay.
I think there are like sequence to sequence papers on machine translation where people have shown that Facebook has shown that you can get away with convolution based architecture,
Right.
kind of probably beat LSTM, but it's a tricky thing to like fine tune or find the proper CNN based architecture.
Okay.
Yes.
What's the training speed of the CNNs versus the
Oh yeah,
LSTMs?
I forgot to. So, like this one took probably on a 100-hour training set. This took close to 15 hours to train for 15 epochs, and this one is 9 hours. So probably 70% less.
One question for you and Ruchi. Did you adapt the multilingual system, or did you start?
No, this is just
from
purely
scratch?
monolingual.
Everything
Yeah,
multilingual.
focused only on improving the end-to-end architecture. We did not work on the multilingual aspect of the Teams code. So so we want to explore other variants of encoder architectures by using multi-band or multi-stream style techniques, and we want to improve on the CNN based architecture, and I think Lucia already presented the RNNLM stuff. So probably so the conclusion is using multi-encode architecture we were able to get a significant improvement. We brought down the character rate from 44% to 34%. That's close to 10% absolute improvement. And when you guys are trying out the multi-encode architecture for end-to-end ASR, it's what we found out is hierarchical combination seems to work. In past we tried combining at the encoder state, and that doesn't seem to improve. So that's one conclusion. And having a diverse, like encoders which are diverse, seems to be beneficial. Ruji showed using different sampling rate, Ruji trained an encoder with different subsampling rate. That's one way of getting complementary information. But you can try several other things. That's what motivated us to explore the CNN-based architecture. So that's the conclusion of our sub-team.
So next topic is some minimum word error rate training for library speech purpose. So this is the joint work with Hiroshi, Kazuki, Rohit, and Shinji. So basically, the attention-based sequence-to-sequence model typically trained by optimizing cross-entropy criterion. So this means that the maximizing the log likelihood of training data like this equation. But this training criterion does not match the metric of interest. It means what we usually try to minimize word error rate. So the goal of this work is to optimize loss that minimizes or is correlated with minimizing word error rate. So this is the loss function based on the minimum word error rate training. This is the expected error rate, and where the W indicates the edit distance between the predicted level sequence Y and the ground truth level sequence Y star. And this expected value can be computed using the sum all over the level sequence Y of the probability weighted by the edit distance. So, but so minimizing this expected word error rate directly is actually intractable since it involves a summation over all possible level sequences. So here we use the approximation based on the n-best list. This is simply replace this all possible level sequences with the n-best list obtained by the decoder. So in this case, so we just limit the number of hypotheses considered in computation of the expected word error. And also we need to renormalize the posterior probability of each word level sequence. So we got some good results by applying this minimum word error rate training on the library speech task, which is read speech of audiobook data set in English. So we have some test sets here. So in this case, so this is the cross entropy baseline of word error rate. And if we applied minimum word error training, we got some nice improvements like this. So usually we got some 6% to 8% relative error reduction. Okay. So in this case, we just use the top 4 hypotheses to compute the expected word error rate. And also we add cross entropy loss mixed in with a weight, small weight, 0.001. And all the variations are done using a beam size of 8 in this experiment. So, and during this research, we also investigated how to generate the good hypothesis and efficiently. So actually, compared to the cross entropy training, we need to generate n best list during training. So this is actually very computationally expensive. So in this work, we try to make our beam search to work in batch processing on GPU. And during the beam search, so we try to keep the computational graph and obtain the n best list. Then we compute the expected word error rate, and then we backprop through all the network. And so by using this batch processing, so we modify our beam search algorithm to make it work in the batch processing. So each hypothesis has kept in the batch processing and synchronously processed in the beam search process. So this is actually ongoing work, and now testing the implementation, and we got already good results. But so yeah, we just confirmed the algorithm works correctly. So when we use the batch size 48 with beam size 20, we got 65 word error rate. So, and we also got the same word error rate when using single normal beam search. So we just confirmed that this algorithm works. Okay, so the conclusion and future work includes this. We got a significant improvement by using minimum word error training. And, but actually, this experiment was done using LAS method. It's a basic attention-based encoder decoder. And the experiment was basically conducted with a Google ASR system, not ESPnet. So we are now, actually we already implemented this algorithm in ESPnet. And now we are trying to reproduce the same result using ESPnet. And the future work includes evaluation using ESPnet. And we try to apply our batch-based beam search for faster minimum word error rate training. And also we plan to do a joint minimum word error training of CTC attention and language model. Okay, that's it. Thank you.
Thank you. Takaaki, while you're changing, can I ask you a question?
Yeah.
So, since you're doing minimum error rate training, do you have a sense for what the average error rate on your training data is, and how does it compare with the error rate on the test data? I mean, I guess you're getting a measure of the training error already, but because it's
usually, yeah. But we are testing the validation. We have a validation data during the training.
No, so what is the comparison? Are they both 6-7%, or is one more than the other? I'm trying to get a sense of whether.
For training data, actually, we got more big reduction.
Right.
Yeah, because always the minimum error rate is optimized for training data. Yeah, and the difference is actually 10% reduction difference between.
So let me tell you what I'm getting at. So because you're doing n-best minimum error rate training, you're not going to overfit your training data because the lowest error rate path may not be in the top 4, 5, or 10.
Yeah.
And the temptation is that to do minimum error rate training right, you should increase n. But increasing n also causes overfitting because you'll then go for the best error path in your training data and not generalize. So sometimes n-best actually saves you. So my question was, what is your error rate? Your error rate on the test data, we saw the numbers. What's your training error rate? Is it lower, higher, about the same?
So you mean the
On-
n-best?
Yeah, on the training data.
On the training data,
Your expected error rate, your objective function.
objective function. Yeah, we will try to express the error rate of the variation of the data.
It's still less.
Yeah, still, yeah. So we always get the n-best list dynamically.
Right.
And we always use the good n-best competitor. And it works very well. And yeah, for training data, we always get good error rate and it can be decreased successfully.
Okay, thanks. We can talk more after. Thanks so much. JJ, you're on.
Yeah, okay. I'm JJ, PhD student at JHU, and this work is done by myself and Hirofumi right there, and also Karthik, Hainan, Takaaki, and Shinji. So these are the people. And I'm gonna explain training and decoding schemes in multilingual SR, and also advanced way of cold fusion called feedback fusion training. And then Hirofumi will do the advanced schemes to use RNN-LM. So motivation of this research is we want to use better RNN. We want to use RNN-LM better so that we can leverage the unpaired text data. And also there have not been many successful methods of using a language model compared to hybrid system. So we want to explore more on this. So I will present cold fusion experiments in comparison to simple shallow fusion method in multilingual SR. I also will talk about field fusion, which is an advanced idea from cold fusion that defeated original cold fusion in both CR and WER. And this is the preliminary experiments. So if you look at the graph, and the blue line is just decoding without language model, and the orange line is decoding with the language model. And overall for Babel languages, we got consistent improvement. So this was just using a simple shallow fusion, combining the scores from end to end with RNN-LM score, just simple way in decoding.
So, JJ, can you say a bit more? What do you mean by shallow fusion?
So shallow fusion is you will get the score each time from sequence model.
You mean for the entire hypothesis, or?
Not only the character level.
Character level. So
Yeah.
you're advancing in your decoder.
Yeah.
You're going character by character, and you
Yeah.
get a score. Okay.
And then also you just sum this with the weighted score from the RNN-LM,
Okay.
also in character level. So
Actually, all the, our RNN-LM, if we don't specify, that is shallow fusion.
Okay.
Yeah.
So it's a standard way of using the
Exactly.
RNN, and you have to use it.
So one thing to notice is also RNN-LM is trained separately with the sequence, and then only use decoding
Right.
trained with. Yeah.
In other words, when your sequence-to-sequence model is trained, there is no RNN-LM in the
Yeah.
training.
Yeah, that's
so
true.
it learns to decode without any RNN.
Correct. Yes.
Without any language model.
Yes. So comparison experiment. So we want to also use language model information when we train the sequence model. So we try to use cold fusion that was already published in, by Baidu. And briefly, cold fusion is a method of training sequence model using pre-trained language model. And in the paper, they use this method to adapt English actually in one domain to another domain, but the language was same. But we want to adapt, we want to apply this to our multilingual ASR so that we can transfer learning from multilingual ASR to specific target language. And actually, in the paper, it showed. So one of the reasons we use this this method for multilingual ASR is it helps train a better sequence model in general, and was able to fine-tune parameters to new domain using less data. So we thought we could use this for multilingual ASR. And so this one is that experimental result that I showed you in the previous slide, but for only Swahili. And I did a cold fusion training for 1,500 hours data in Swahili, and then it was actually dropped to 52.9 compared to the shallow fusion. The orange line is shallow fusion. So I also want to report this result. So when we actually do the shallow fusion training from a specific parameters, for example, the second row is cold fusion transfer from multilingual SR, and the third one is cold fusion transfer from Scratch, and fourth one is the cold fusion transfer from transferred model. That's basically model that was fine-tuned by Karthik. Actually, this is just simple transfer learning method. And then we compared those results in WER. Actually, we observed that actually from multilingual ASR parameters, cold fusion works the best. So here we say the starting point is using a proper parameter pre-trained is actually important in using cold fusion in multilingual ASR. And then when we decode the model, we all use the shallow fusion way in addition to, yeah, just use this.
Can I ask a question? In the Lucia presentation, you said that Aaron and Alan didn't help him at all, and now you're telling us that Aaron and Alan helped you a lot. So what's the difference here?
The language weight that I put is 0.3, and it's smaller than where the UJ is reported. Like I use small language model weight for my experiments.
Yeah, because there's two different message here. So like, yeah, what that mean? What that mean?
So
it's less weight, but that what it mean?
I don't know. You didn't get any improvement, or?
Yeah, it's like 0.1 or something.
It's 1%.
Okay, 1%.
Yeah, 0.1.
So so depending on the noise, how much noise you have.
Did you use his same art? Did you try at least guys compare together and use the same architecture maybe because you're not using the best system, that's why and it's helping you or something like that?
So for this one,
this is a huge improvement, but like, it doesn't show it.
Yeah, 5, 10, 20, 50 hours, right? On the axis, on the x-axis. So I thought, well, within this range, using RNN-LM will help. So I try to use the RNN-LM, but sometimes, if depending on the amount of the noise in the data, if you actually increase the language model weight, it actually gives some more gain. But like he said, he was using just 0.3. So for example, I didn't put the result here, but if I use 0.7 for language model weight, it actually went down to 0.2, 0.1, as I remember. So intuitively, if you have more noise in the data audio file, then you will maybe put more weights on the language model prediction, so that it can help the noisy condition prediction. So yeah, that's, I hope that it's that. Yeah. Anyway, so so this is the architecture of cold fusion. So first we get the state from the sequence, and then we get the logic, which is before the softmax, and then went through this to DNN to map this to this hidden, this new representation H, and then we merge this H and S, and then push this through the gate, and then we get the gate representation, and then we do the element-wise multiplication with H, and then again we concatenate this with the ST from the sequence, and then we get the cold fusion state, and then do the DNN, and then softmax we get the new prediction for YT. This is the cold fusion architecture. So this one is the equations. So you just put the logic to DNN and then get the HT, and then concatenate this second row, concatenate ST with the HT, and then put through DNN and do the sigmoid to get the gate. And then you do the element-wise multiplication with HT with gate. And then you concatenate again with the ST from sequence, and you get the cold fusion state. And then you push this through this again to DNN to make this dimension same as your character size. And then you do the softmax for that, and then you get the final result. And I was thinking, so in this, why, so in this case, we don't update the sequence state. Yeah, sequence state by the cold fusion state, which I think has more information compared to the ST. So I was thinking that why don't we use that cold fusion state to update the sequence model state. So we do some variation in cold fusion, and we will call this feedback fusion because we use the feedback of the cold fusion for the updating the sequence model update. So I will call this through call this feedback fusion through this presentation. And this was our original cold fusion architecture. And we don't update this sequence by that pointers, but instead we have new pointers from the cold fusion state, and then we give this back to the sequence. So if you look at so all the red boxes are actually added parts, and all the blue lines are the newly added connections. So because I was using LSTM, this looks a little bit complicated. But basic idea is, you know, if you look at this solid line, you will get the state update from this cold fusion state. And for example, if you do this with the GRU, you don't need any connection and any red boxes connected with the dash line. But because this is LSTM, I need to do more for that connections. So this is the equation. So right now, you calculate the third row. You calculate the gate for the cell also, and concatenate this to get the new cold fusion. This is not a cold fusion state, but before the cold fusion state. And you put this to the DNN to make the dimension match it with other components, so you get the cold fusion for state and also this cell, but this cell is not used for calculating prediction, but only ST is state is used for calculating prediction. And also, when you update right side, when you update the LSTM state, now we are using state and cell from cold fusion, and then you will update the next state and cell. So this is the final result that I got with the repeat speech. So if you look at this, I will get a large gain from this shallow fusion. Baseline is shallow fusion to this cold fusion training. And then if I apply the feedback fusion, then it will get like a little bit more gain from that. So it's basically improved the cold fusion. So, okay. So this is character error rate, and this is word error rate. So, yeah, our conclusion is transfer learning using cold fusion started from actually pre-trained multilingual SL model works better than shallow fusion. And feedback fusion has extra gains compared to cold fusion. And future work will be apply feedback fusion in multilingual SR, and also combine techniques from other members to compete with conventional hybrid model. Yeah. That's it. And then Hirohumi will take over.
Hi everyone, my name is Hirohumi Inaguma from Kyoto University, Japan. So I'd like to talk about the initialization of the decoder part in the sequence-to-sequence model with pre-trained language model. So while cold fusion is a kind of language model integration method, this method is a kind of transfer learning from large text data. So the advantage is that we don't need to change the architecture of sequence-to-sequence model, and also we don't need to increase the number of parameters. On the other hand, the model may erase previous knowledge from a language model. So we can regularize sequence-to-sequence model with language model objective or combined with cold fusion. So we compared the language model initialization with cold fusion, also combined with together. So we evaluated with every stage clean 100-hour data. Language model is trained with the whole text data. As you can see from this table, simple language model initialization outperformed baseline shallow fusion. But in case of combining with language model objective, the performance was degraded. I think this is because we shared the parameters of language model with the whole decoder part. So I think we should calculate losses of language model from the lower layer of decoder part. Also, cold fusion was the best system among these systems, and in case of combining with language model initialization, performance was degraded but better than baseline shallow fusion. So we can conclude that naive cold fusion is the best, and the combination is not effective in the current architecture. So in the future, we will extend cold fusion and language model initialization to other units such as word or word-based units, because word level language model is better than character level language model. And also extend to low resource SR, where multilingual language model is integrated into the decoder part rather than monolingual language model. Also extend to multilingual SR, where multiple language models integrated in the single decoder part. For example, monolingual and multilingual language model. Because monolingual language model has language-specific information, but multilingual language model has language independent information, so they have the complementary effects. That's all. Thank you.
Okay, so next topic is exploring beta units for end-to-end speech recognition. So this is a joint work with Jiro, JJ, Sanjeev. And from, so I will talk about incorporation of word-based RNN language model into the end-to-end speech recognition, and the other one will be presented by Jiro about exploring sub-word-based end-to-end SR. So actually there is a unit issue in end-to-end speech recognition. So end-to-end model can train any kind of input sequence and output sequence pairs. And actually we can choose any kind of output sequence in this case. So for example, we can use character sequence as output level sequence, and we can also word sequence like this. And also we choose some subword units. This is a kind of in-between approach. And so just we can train the model using this kind of output level sequence. But we actually don't know what unit is the best for the end-to-end SR system. Yeah, this could be dependent on the amount of training data or target language, but we need to select a good unit for end-to-end SR. So I will briefly explain about the each unit. So when using the character sequence, good thing is it's easy to run acoustic mapping with a small amount of training data. Actually, the number of characters are much smaller than words or other units. But so usually it's difficult to run linguistic constraints over long sequences. On the other hand, if we choose word units, so it potentially has a higher accuracy than character-based system by running word-level linguistic constraints. But usually it's difficult to run acoustic mapping with small amount of data, and also we usually have out of vocabulary words, so it's a bit difficult to handle by just using a limited amount of training data. And the subword approach is actually this is very promising approach, and this approach was actually scalable to the size of training data. So we can choose any types of subwords. We can choose the number of subwords. But usually we need to find good units based on some chunking algorithm, some automatic methods.
Sorry, question?
Yeah.
I would have expected on the previous slide, fourth bullet point, which would be phoneme units. You know, people used to use pronunciation dictionaries. Are those totally gone? Or something, some pronunciation model that's learned?
Currently, yeah, we just focus on the end-to-end style, and we only have a grapheme information when training the model.
So when you say in the second bullet point, word-level linguistic constraints, are those word-level linguistic constraints the pronunciations of individual words?
Yeah, but end-to-end scenarios, we don't have a pronunciation lexicon.
But you could learn one as a latent variable, maybe?
So
You said there's no external resource for a pronunciation dictionary, but that doesn't mean you couldn't learn one as a latent, learn pronunciations as a latent variable. What do you mean by word-level linguistic constraints? Do you mean knowing that through doesn't have a G sound in it?
We just assume we don't have a pronunciation lexicon, but so you need some latent phonetic information can be trained using the word level units to use.
I might expect you would relate speech to phonemes and phonemes to words, and those would be different levels of the system, even if you have no supervision about the phoneme. Mainly, I was just asking, when you say word-level linguistic constraints, did you mean pronunciations or something else?
Yeah, just I'm saying that the linguistic constraint means that word level more grammatical thing.
Isn't that in the language model?
Yeah, it's so that the sequence model has includes the linguistic prediction part, and word level information is quite important to predict the double sequence. So when only using characters, it actually don't present explicitly the word information in the model. So yeah, this is just I'm saying the word level constraint should have more informative about the language, linguistic information. Yeah.
Thanks.
Okay. Okay.
This was my question.
Okay. So our model has a language model part in the encoder-decoder, and where we assume that this language model predicts the same unit as the decoder network. And we usually predict the character sequence, together with the attention decoder. But in our low resource language scenarios, the amount of paired data is limited, but language model can be trained using larger external text. So in this work, we try to combine the character-based decoder and word-based language model. So where we try to exploit both benefits of character and word units. And so we propose a look-ahead word RNN language model here. So the look-ahead word RNN language model is a kind of very old-fashioned ASR approach. So here is the objective of the decoding, and we try to find the best character sequence using the CTC and attention model and language model scores. And here we want to use the word level language model score for this part. But the word language model score can be applied only at the end of word, where the word identity is determined. So actually, this is too late to keep correct hypothesis in the beam search process. So we introduce a look-ahead technique to apply word LM scores as early as possible. So we use this type of technique using the tree lexicon representation. Originally, this type of technique was used for n-gram-based decoding, but we tried to apply this mechanism to the RNN language model. So here we want to give a score to each character sequence during the decoding. So we compute the probability to each transition in this tree dependent on the context. So we compute the look ahead word LM probability using this tree. Actually, this look ahead score is computed using the sum of the probabilities of words that can be reached from each node in the tree. And one big problem is actually the computational cost for needed for getting the summation, but this part can be computed very efficiently using pre-computed cumulative sum over the softmax distribution. So just adding one operation, cumulative sum, just right after the softmax, we can easily compute the summation of this probability. And this is the result of WSJ. So by applying the character-based language model, the word error rates successfully decrease like this. But if we just replace the word character-based language model with the word language model, the word error rate increase like this. But we use our new technique, look ahead language model. We finally obtained the 5.1 word error rate. This is actually the best number published in conferences on this task. We also evaluated this technique with library speech corpus, so we also get some better results than when using the character LM. We got almost 10% error reduction. Okay. So next topic, implemented.
Good morning. I'm Shiro Nishitowa from Red River Corporation, Japan. Today I'm talking about the improvement of ASR model by using subword units. As Takaaki noted, character model is easy to learn acoustic mapping, but it's difficult learning linguistic constraints. On the other hand, word model is easy to learn learning linguistic constraints, but it's difficult to learning the acoustic mapping. There is a trade-off between them. So we propose to use subword units. Subword unit is using subword unit is popular in neural machine translation. For example, hello world in the character model, hello world is segmented to H, E, L, L, O space W, O, R, and D. In the word model, hello world is hello and world. In the word model, for example, hello world is segmented like this: H, E, L, L, O, and world. There are several ways to segment some word, and good segmentation is acoustically more expressive and resolve out of vocabulary problem. So there are two novel approaches to make subword units. First one is subword segmentation with unique language model. And the other is based on back-pair encoding. Subword segmentation is unigram language model is the overview of subword segmentation with unigram language model is like this. First, generate many subword candidates by most frequent substrings. Then new subwords that uses Unicode language model score. The overview of byte-pair encoding is like this. First, initialize subword vocabulary with the characters, and then count all symbol pairs and replace most frequent pairs to a new symbol. You repeat these two processes until you can get enough subwords. We propose to we use subword segmentation with Unicode model. We experimented with these two datasets. First one is Libre speech English dataset, and second one is CSA in Japanese dataset. This is the result of Libre speech. It is good performance than we can get good performance than character model with subword units. This is the result of CSA Japanese dataset. It is slightly worse than character model. We also experimented multilingual data in JSLT 18 but this is still running. Accuracy is growing up and losses becomes smaller. Using subword units is also improvements efficiency of training. In the Libre speech dataset, we can use 43% of training time, and in the Japanese dataset, about 20% of computation time is reduced. These are future works. We need to some other number of units of Japanese datasets, and we also experiment. We are going to experiment with multilingual dataset. Okay, thank you. That's all. Thank you.
Thank you, Jay. Something that said Oliver earlier.
Yeah, that was an old version.
Oh.
Whatever you've got on your computer is the most latest we've got.
Should bring your laptop if you need to.
Yeah, no, if you go to your directory locally, as in Hi, I'm Oliver. I'm a new postdoc here in the CLSP. And this is some work bringing in some phonetic and phonemic information that was done with Matt and Yenda. So the motivation for predicting phonemes or phones, the grapheme sets often do not overlap between the languages. And when they do, symbols may correspond to substantially different sounds. In contrast, many of the phones are shared between languages with different orthographies. And so predicting units like these may encourage better representation learning and also allow some sort of meaningful form of transcription of languages whose script we haven't seen in training. For example, in our set, we trained on 10 Babel languages, and Lao was not in the training set, but didn't have a script that was common with anything in the training set. And it's also relatively cheap. If we have a pronunciation lexicon, we can just use it and use G2P to fill in the blanks. So this illustrates the different orthographies we have in some of the Babel data. And in the black or the grey are the orthographies, and then we have X-Sanford in the green, which has a lot more overlapping units. So I'll discuss two approaches. The first was a preliminary look at grapheme prediction across all of the multitask objectives. That was done by Yenda. And then I'll discuss predicting graphemes and phonemes separately, which I did in conjunction with Matt. So the idea behind the graphemes is that instead of predicting graphemes, we predict symbols taken from this Cartesian product of graphemes with phones, or more than one phone in the case of pronunciation ambiguity. So here in the black we have the graphemes, and in the green we have IDs corresponding to phones, and they form one unit together, and you predict them. And when decoding, you simply discard the phone ID. Yen did some experiments on 100 hours of LibreSpeech training data, and there was an improvement using graphones over graphemes. That was in the monolingual case. But on Babel, the graphones perform about 1% worse on average. There's a few possible reasons for this. There might be a bug that hasn't been resolved yet. The Babel languages may already have a pretty good correspondence between graphemes and phones and might not get the same benefit that English does. And also using these graphones introduces data sparsity in a multilingual context, because you can't share phones or phonemes between languages. So something I explored with Matt was to keep the attention decoded predicting phonemes, but replace the CTC grapheme objective with a phoneme objective. Or actually, we just added another phoneme objective and a weight corresponding to that. And this has the potential to better bridge the representation learning between languages. So here's how it looks. In the red, we have a CTC phoneme objective, and in the blue, we have our attention decoder, which predicts graphemes with a shared encoder. And we may also have another CTC objective for graphemes, which is sort of representative of the standard ESPNet multitask framework. Now, this is some the validation accuracies during training of our model on the Babel data. And the grapheme weight is how much weight is put onto the grapheme CTC loss function. The phoneme weight is how much weight is put on the phoneme CTC loss function, and the remaining weight is put onto the actual attention. So the orange line is just focusing on the grapheme attention. The blue line is just grapheme attention and the grapheme CTC. And the green line is no grapheme CTC, but the grapheme attention and the phoneme CTC. Now, the phoneme CTC performs better than the grapheme CTC during training, but actually just focusing on only the attention of the graphemes. Attention loss for the graphemes works best, which is not that surprising during training. but what's interesting is happens at test time when we're doing full decoding with the beam search. The order almost stays the same, except when we're doing the beam search, we can introduce the CTC probabilities as part of this hybrid decoding. And it's in that case that it's actually the multitask grapheme, CTC, and attention that performs the best. And the role of these CTC probabilities in decoding is very large. Unfortunately, we can't straightforwardly use the phoneme CTC probabilities in decoding in the same way we use the grapheme ones, because they're probabilities over different units. And so using the phoneme objective didn't yield any positive results across any of the languages we looked at. On the other hand, it lets you decode phonemes, and so we added just some basic CTC decoding, and we can transcribe the phonemes of languages we haven't seen in training and whose orthography we haven't seen. So in conclusion, CTC probabilities used in decoding are very important, but unfortunately the phoneme CTC probabilities can't be used in this framework. However, some other combinations of weight may show better performance. At the moment we're running some experiments which uses the attention, the grapheme CTC and the phoneme CTC, and that way we can leverage the grapheme CTC probabilities in decoding, and maybe in that context the phonemic information will help, but it might very well not. But now we have phoneme objectives implemented in ESPnet along with corresponding recipe for some future experimentation. Thank you.
Hi, I am Martin Grafiat, and I will tell you something about multilingual approach and how we put that multilingual information into the system, that's sequence-to-sequence system. So we have all the two teams, and I will focus on this first part mainly, like investigating models, architecture, and training methods. So it's well known that end-to-end system or sequence-to-sequence system are pretty sensitive on the amount of training data. So we ran a few experiments on the basic experiment on the Babel language, and we found it's really a lot, right? You can see if you have 50 hours, it's full Babel set. We have performance that if you have this amount of data, you are getting lower and lower, especially between 20 and 10 hours and 5 hours, it goes completely wrong. So the system is completely unusable. So the dependency on training data is really huge, so we want to solve it by adding some multilingual information, because systems generally suffer because the sequence system is trying to estimate directly probability of output sequence with given features. In compared to standard HMM-based system, they use so they use pretty effective factorization of the problem given the sequence and the feature by factorizing to given features and sequence multiplied by given probability of sequence, where the sequence is factorized again to the words, phonemes, and lower unit. So the problem is split into small parts, but generally this is a bigger problem for the sequence-to-sequence systems. So we hope that multilingual approaches can partly cope this problem by sharing the knowledge from other languages. So what we decide to play with it, because of course you can multiply that multilingual approaches on few levels. We play with the feature level, where it's pretty obvious because all humans share the same vocal tract, so it's definitely possible to generate the features which just emphasize the human specific or human knowledge on the higher level. And these high level features could be put into the systems. And the next is model level, so it can easily jointly train model on all training languages, and after you can just run some fine tuning if it's possible, or just transfer learning to the new language. Or of course you can do combination of both. So architecture, which was a few times said, so we have like waveform, feature extraction, and model, and we have a lot of other languages which can use. In our case, we train on 10 baby languages, and we took the other languages as unseen language. So we can use these 10 languages as the helping for feature extraction, or the acoustic models, or both. So first, it's a feature level. We decide to take pretty basic our bottleneck extraction, where as it's training on separately from the sequence-to-sequence system, it could be trained in traditional ways using the GMM alignments on phonemes or characters. We play with both. Of course, we go to the better with phonemes. We use standard frame level randomization with blocks of multi-output layer. And we train this convolutional stack bottleneck architecture, which is multi-hierarchical neural network architecture, and you have like 2 layers. First is reading the short context. First part is reading the short context, and after it's run the convolution with trait 5 on the wider context, and it's going to next layer, and this is our output. So when it's trained, it's pretty easy to just say, okay, we train it on languages, and after we can train exactly the same system like before, only instead of filter banks, we use this multilingual.
Before we just back up for a second.
Yes.
So the blue part on the right, that's language specific, or?
Yes, this is language specific. We use like blocks
and
of marks.
everything to the left of that is?
Yes, it's language shared, hopefully.
Good, thank you.
Yes, we also play with single bottleneck. But I got results pretty late, and so they are even slightly better if you just single bottleneck, and after you have shared knowledge. And cross-validation looks worse, but when we use other other features, we got slightly better. So with some higher level or lower level is still something important, because these architectures are having better a lot of part of the low level feature information. So when you train the sequence-to-sequence system on this feature, we got pretty impressive gains. It's about 3%, so from 1.6 to 5% improvement. Interesting is that, for example, Swahili and Assamese is unseen languages, but Tokpisian and Georgian is seen languages. So they were the part of the multilingual training features data. And you can see that actually doesn't matter. The improvement about the same. So the features are already pretty generic. And the interesting is that in the low amount of data, you can see that right now it's completely not destroying the system if you train only on 5 hours. You can still see that, of course, you are getting degradation, but the degradation is not so drastic.
So when you say, let's say, 5 hours in Swahili,
yes.
What about the other languages? Do you also have only 5 hours in those, or do you still have the full complement in the other languages?
What do you mean? Because features were trained on 10 hours, right?
Oh, I see. Okay, the features were trained on 10 hours of everything. Okay,
yes,
correct.
The features were trained on 500 hours.
And then just the sequence-to-sequence model training has 5 hours of
yes.
Okay.
But the features haven't seen Swahili and Assamese.
That's all right.
They see only Tokpisian and Georgian. Okay. You can see that it doesn't matter so much.
So what are the performance of the hybrid system, Asian analysis?
This is character rate, right? So it's not so easy to recognize it. It's like phoneme recognizer. So you can score it on this, and before the guys show it's an iron and LM decoder. So it's about 10% more. But when you play on Babel, yeah, you cannot see. I don't have water rate because it's phonemes, actually. Okay. Next part is the acoustic model. We used character level system. It was pretty easy to just put all characters together and train on languages together on standard filter banks. So it's pretty straightforward. It's just trained in 500 hours jointly. And after, you can just take language which was in training data and just decode with it to see if it helped or not. So we took Tok-Pisin and Georgian again, which was trained languages, but you see pretty huge degradation. So we were interested, why is it? And when you go from the output, you see that sequence-to-sequence system can predict the language, but it's not 100%. We found about 80% and 20% just wrongly define the language instead of Georgian. It said, okay, it's not Georgian, it sounds like Vietnamese, and generates the Vietnamese output, and it cannot recover. When it starts with Vietnamese, it starts keep going, and so it generates complete wrong utterance. And in the other case, we found like this thought that it's Pashto, and it generates Arabic characters instead. So we are getting a lot of errors. So how to remove these errors? So of course we can add some language ID information, but when you want to do a completely new system, now it could be pretty difficult because you have some language ID, you need to generate it. So we were thinking about much easier approach because in general you have like equality of the training language, so system doesn't know which to focus on. So we just say, okay, when the system is trained, you can just run a few more epochs on your target language, which should strengthen and make stronger. So system should prefer the target languages. Or we can train the language transfer learning, which basically means that we rebuild the final layers completely on target language, and the system cannot do these confusions. So this is how it actually looks like. Again, the Tok-Pisin and Georgian, which is only the source languages from the training data, and this is from Swahili, which is unseen language. But Swahili used the standard Latin writing, so the characters were in the part of the training data. You can see that it's the same, right? You got degradation, but after this few epochs, you can see huge gain over the monolingual system. And when we tried to look at it, there was no any language confusion. So the system was pretty sure that this is Swahili, or Swahili, this is Tok-Pisin or Georgian. But for Swahili, it's pretty interesting, the result, because of course you can decode just with multilingual neural network is completely wrong. See characters, but never have seen any part of the Swahili, so it produced something completely wrong. But when you add only 5 hours of the Swahili data, it's right now it started working pretty well. So the system is getting focused on Swahili and work pretty well on Swahili. And if you're adding more and more training data, it's of course getting better. And finally, it's still better than the baseline.
So what do you especially mean by fine tuning?
You just run a few more epochs only on target language. Because on beginning, when you train the multilingual system, you train on all languages. So each.
So how do you want to to make sure that the gradient don't go too far, because the first line is always
yes, of course, you don't go far. So I run only few epochs only on target language. During multilingual training, each utterance is going from different language.
And you're training the whole network again, featuring the whole network, or only part of the network?
Whole network. Because the starting point is pretty important.
But why? Is it an encoder decoder?
Yeah.
Yes. Why you don't go fit only the decoder?
Yeah, I will continue.
Okay. Okay. Sorry.
But if you will not have characters in the target language, you cannot do this simple fine tuning. So you have to play with the rebuilding on the decoder. So, but system is pretty complicated. You can play on many levels. You can just rebuild the outputs of TMAX, or you can rebuild the outputs of TMAX plus CTC, output with the attention, and you can rebuild everything after the encoder. And first, these parameters are initialized with the random, so you need to train only these new parameters and freeze the remaining. And after, you just can retrain a bit the whole network and see how it works. So when we did it, we found that it's pretty useful to retrain only the output part, because the rest is still from the multilingual pre-training, so we are getting some gain. And the improvement from this is about between 1.2 and 4. So it's pretty similar improvement from the multilingual features. You can see, for example, for Swahili, all these techniques what was presented, so it's monolingual. After we have fine-tuning, language transfer, which is for Swahili pretty interesting, because you, right now in fine-tuning, you have output characters, but you remove them and start from scratch. And you can see how it looks at. You see that it's pretty similar between fine-tuning and language transfer. It's about similar performance. And unfortunately, the best things what is just train on multilingual features and that's it. This is where we got the best results so far.
But okay, until this point, Swahili still has a character set overlap with the training languages, right?
Yes.
It's not. It's just that you haven't seen Swahili in the multilingual training.
Exactly. Yeah.
Right.
There was just characters.
Look at a language where even the character sets are non-overlap. Like you said, Lao maybe, which was the one that.
Lao, Mintok Pisin or Georgian?
No, didn't you have one
Lao
language?
was also there, but I didn't play with Lao.
Okay. You said you had one language where there was no overlap, or maybe it was Oliver who said it, that there's no overlap in the grapheme set either.
For example, it was Assamese. Amharic.
Amharic.
Amharic is a special character. So we cannot play with it because this is completely different characters from the training. So we can do only the transfer learning.
Okay, all right.
And this is same comparison for other languages. Where of course we cannot do the fine tuning for Amharic because this is completely new character. So you will see number over 100% definitely. But when you compare it, you can see that still the building of monolingual system on top of multilingual features working the best. But the gains where we are getting from multilingual system doesn't matter if it's language transfer or fine tuning. It's pretty similar. It's slightly worse, but it's not so much. So naturally, we should play with the building multilingual system on top of multilingual features, which they should gain from both of them. But there was some bug probably because till now we still haven't got better results from it. And I got the result pretty recently, so I still have to spend some time with it. So it's some for future work. So just to conclude it, we found that multilingual feature extraction and acoustic models are giving similar gain, but feature extraction is slightly better. Interesting was that fine-tuning of neural network is performing really well, even if you have almost really small amount of target language data, and that language transfer is giving similar gain to fine-tuning, what is said, and of course we have future work to play with that multilingual system on top of features. Yes, that's it.
Thank you.
So we will have a 10 minutes break, and we'll restart the presentation from the 10. Yeah.
11, 10 minutes.
I'm sorry, 11, 10.
All right, time to stretch. 2 hours is That's not again. Please.
Yes, go ahead.
Yeah. Good morning, everybody. So.
Take your seat, guys. Take your seat, guys. All right. All right, go ahead, guys.
Yeah. So in this presentation, I will be just presenting the work, what we did for this workshop. In my case, I will be especially concentrating on the techniques which we use for improving attention-based models specifically, and so we try to explore some important architectures, changes in architectures, and different training schemes for building a sequence-to-sequence model using attention-based systems. So first, this was the idea of the workshop, to have some incomplete data, and in my case, I will be trying to use some moderate size source and try to reduce the error, reduce the character error. Okay, so first, after coming to the workshop, I tried to decipher what is this multitask learning. They try to use CTC and attention from Shinji's model, and we were having this baseline initially with CTC plus attention, and I tried to decode it across different kinds of data, and the data is listed in chronological order across different data sizes.
These numbers are character rates?
These are still character. Okay, I will just caution you that all these are character rates. I don't say any word arrays. Especially in the final slide, I can show one or two. Okay, so these are listed in chronological order, and you can see the CTC plus attention is quite standard across different level of databases, but also CTC is better. But in case of attention, there was a quite difference in performance, especially when we have very less data. This is at least okay. But in case of Oxford, which was 14 hours of data, we got a drawback in performance. Whereas in Swahili, still it was around 40 hours of data. It improved, but not like quite significant. And in case of 80 hours, the attention was able to do something, and it was even better than CTC. So we tried to
just so that I remember the pictures. So this picture we had earlier was that you had your encoder-decoder model with attention, and then after the encoder you had the side path which went through CTC.
Yeah.
That's the picture. Those are the two blocks.
Those are the two blocks. Yeah.
So it's a common encoder, but on one side.
Yes, exactly.
On one side you have attention followed by
yeah.
decoder, and the other side you have CTC blocks based.
Yeah, exactly. So we trying to focus on these two languages because it was out of my interest. I tried to improve the attention performance for these two languages. I'll just show the techniques what I tried to use through the workshop. The first one was the schedule sampling method. This was especially used in NLP as well as in speech recognition, and we tried to just follow the same procedure in sequence-to-sequence approach. So here we try to use the predicted embeddings to the decoder at random time intervals. Usually we use teacher forcing approach where we feed back the true embeddings, but we do this we feed the predicted information just to get better generalization, especially during inference procedure. And the decoder actually benefits from this a lot. And the experiments we did, we tried to use 50% of the distribution from predictions as well as 50% distribution from true embeddings, and we got good outputs from by using the schedule sampling. And this one was without schedule sampling. The sequence of predictions were quite good, and also the performance improvement was quite significant across all these different databases. We were able to, especially for Oxford, we were able to improve from 39 to 14.8, which was quite drastic. Maybe we are still suspecting the attention, but the performance was very drastic. And in case of Swahili, it was already 33, and the error rate improved by 1%, but and in case of AMI, it improved by like around 0.5%. And we see that schedule sampling, as the amount of data increases, it reaches a threshold, and the relative improvement is quite less. Whereas for smaller data sets, it's quite significant.
And maybe one more clarification, Karthik. Go back to the previous one. So I know you've been reporting character rate, but your blue and red look like they're word-based. How does the conversion happen?
There was so much space, so I have to put two lines. So I just kept it as words. It's actually character predictions. It predicts characters.
I see. So
yeah.
So that's why there are multiple stars and things in this and that.
Yeah,
okay,
right.
all right. So you put it this way just so that I can read it.
Yes. Yeah. So there was another. So we tried to extend this model in a multilingual setting, and initially we did few experiments, and we were not getting any improvements. But so the idea here is, like, when we try to port a multilingual system to a target language which is completely unseen or seen in the training data, still when we try to port it to a new language, we assume the multilingual system makes some predictions because it was trained with different languages. So to handle this, we try to use the schedule sampling here, because during training we can feed back the predicted embeddings of the multilingual system and ask it to correct based on its own predictions. So this was the motivation to use schedule sampling in multilingual setting, and Martin helped us to run these experiments, and we got this result yesterday. This was the best result shown by Martin in his previous slide, and without using any multilingual features, by just using filter bank features and fine-tuning a multilingual system along with schedule sampling, and there was not even CTC used here, it was just attention. We were able to get like absolute 1% gain across this data, which is unseen, it's a target language, and these two are like training languages. And still there was some gains, and so using schedule sampling, so I guess it might be quite effective, even including CTC along with it. So based on the schedule sampling approach, we made a few observations. One is, like, as I already mentioned, with smaller data sets, it was quite helpful. And the other one is, like, the decoder acts as an implicit language model in case of sequence-to-sequence models. And because we say it as implicit, because we feed the output from attention as well as the previous character embedding from the previous step and try to predict the next character. We try to use a decoder also as an explicit language model in our next experiment, so which I'll be discussing now. So we call it as like prediction-aware language model, which we keep it as a second layer along with the decoder and feed the predicted embeddings as well as the true embeddings. And this is the motivation of this approach. Like, as an attention, we had to use, we tried to use a in-house language model completely trained along with the training data, like paired data. And to do that, we had an initial decoder layer, which by default we have, and then we tried to predict the character embedding from this and use another decoder layer, which just sees the embeddings and try to predict the next character out of it. We tried to use this approach by feeding this character embedding as a true label coming from a true label as well as the predicted labels. And so we did this experiment just for Oxford Italian because it was quite small, and we got the results latest recently. So this is the performance when just feeding the true embeddings to the second decoder layer. We got like we got a word error rate improvement from 48.8 to 42.5, which is this one. And in terms of character rate also there was a slight gain. Whereas if we try to use predictions and true embeddings together in the second layer, there was slight gain in the character rate and also not much gain in word error rate, but still there was absolute 2.8% improvement. So this was the other approach we tried to use. And So some of the extensions which can be made to this approach is, first of all, it's still in experimental stage. We have to try it with much more databases to make it more reliable. And also we are planning it to use this approach by also training it unpaired text in the decoder layer, not just with paired text, but also with some other external text. So the next method we tried to use was mainly motivated by using some auxiliary information to the attention models. Especially people try to use language identification features along with in the sequence-to-sequence training, where language features are trained separately. So here we tried to use the GMM HMM alignments because we had GMM HMM alignments. So we thought, why can't we just plug in these frame level alignments into the attention model and see how it performs. It was just a experiment to test how it works. So we tried to use two different kinds of architectures. One is get the outputs from the encoder and have this alignment layer. So this is just a simple recurrent neural networks which gets these encoder outputs and try to see the frame level alignments and have this information here. Whereas the attention also sees the encoder outputs, but this loss function is just to modify the encoder outputs. Whereas in the other approach, we just tried to plug in the alignment model directly before the attention, so that the attention also tries to see directly the alignment outputs coming from the encoder. So we tried to experiment with these two techniques. And one more thing is, like during training we have these two loss functions, whereas for inference we don't need that. So we just use the character level probabilities.
So Karthik, should I think of this as some kind of multitask training where you're saying predict the character and also predict where it aligns in the acoustics?
Yes.
And during training time you have both, and at test time you're not going to worry about what alignment you're predicting. You just want to
It's an attempt to make it closer to hybrid, but we tried to see how.
It's an attempt to inject additional information in training. You say, I know what the alignments are, so make it predict both during training.
Yeah, just to see like how much it can gain out of it. So this was done with Swahili language. It has almost like 38 character labels, and this is the baseline system what we have right now. And this is the type 1 model where the attention sees only the encoder outputs. We got nice gains, like around 3% gains across all different kinds of models. Whereas with type 2 system, like the gain was much more, and finally we were able to get like 28.4% character rate along with CTC, but even just with attention, it was still comparable, not even with CTC. So the takeaway from this guided attention model is that still we are lagging a lot because the GMM HMM performance is like 46.7, whereas this model gives like 55. It was able to benefit a little bit, but not like as we expect. Not completely. It cannot utilize all the information. And one problem might be because we are not able to use different mini batches for frame level training and sequence level training, because it tries to have two different kinds of sequences, and so further investigation is required to make this model much more better.
Is this GMM or SHMM use a multilingual feature or something?
Yeah, it uses.
So it's not fair to compare them, right?
It was not. It's not fair to compare, but still, we wanted to see. Yeah, the inputs are quite different.
But this is for Swahili, or which language is this?
This for Swahili.
Trained on the 80 hours, whatever is available.
38 hours.
So they bought on
38 hours. Okay.
Yeah.
But bottleneck coming from multilingual.
Yes. Yeah. It's not a fair comparison, but this is what we had for the current moment. This version. And also, it's a GMM system, so still it's not a fair comparison. Anyway, we're comparing. Okay, so in this I just presented all the ad hoc approaches we can use for benefiting the attention models, especially the attention models. And in case of schedule sampling, it gave significant gains, especially for multilingual transfer learning approaches. And we assume we can use it for all of the target languages. And also the other two models, like having an explicit language model as an additional layer in the decoder, and frame level alignment, incorporating the frame level alignment, was giving some considerable gains. So the future work might be to combine all these strategies and also try to use Ruji's model, which is much better, to see how much we can go to the hybrid systems, comparable to the hybrid systems. Thank you.
So from now on, we move to more about the incomplete data setup. And the first, we will explain about the end-to-end speech synthesis, which is actually one of the big projects in our team. By the way, I have a big pressure of finishing my talk very early by the organizer. So I will try to, skip some of the things, but still I want to kind of give you guys how this kind of research is very kind of exciting. So I wanna focus on here the little bit more like we don't have so many data, or we only have a text only data. In this situation, the following the talk is pretty much focused on the how to kind of making the ASR and TTS the jointly trained to tackle incomplete data, and here TTS is required, right? And the second one, classically people are always talking, if we have a perfect TTS, then from only audio data, we can generate infinite audio data. We can make a parallel data. So that's a kind of important topic in our research, in our team. And for this, to realize this one, of course, we need a text-to-speech component. So this is one of the missing part of our team used to be. But now that we finished to implement text-to-speech.
Text-to-speech.
This comes from our tool.
Text-to-speech.
Okay, so this is mainly done by the Takaaki, and me and the Google, Yu-chan from Google. And I kind of skipped the details about that. But of course, to do everything end-to-end, we actually using an end-to-end speech synthesis system recently proposed by several researchers, including Google. And we are using a Tacotron 2 system, which is again completely end-to-end from the grapheme to the speech features. And we also made it available to the open source through the complete recipe of the ESPNet. And I will skip some of the audio example due to the time, but if you guys want, I can play it later offline. Anyway, we actually can fit the missing bits. Then the workshop, we more focus on how to apply these TTS techniques to some of our project. One is the data augmentation. So as I mentioned, if we have text-only data and if we train the TTS, we can generate a lot of audio data. But here, instead of generating the audio data, we actually predicting the encoder state for the two reasons. One is the computational efficiency. Also, second is the high-level encoder feature may not have a speaker characteristic. So at that time, we don't have a speaker we don't have a multi-speaker TTS system. So to avoid the speaker characteristic, we actually using an encoder feature, encoder level feature as a target. And the result is the following. Successfully, we got a kind of significant improvement from the baseline to ours. But the question is, text data, why not we use the language model? We can also use language model,
Can you
right?
slow down a little bit, just go back
Sure.
one step. So you're going to train your TTS engine
Yes.
to take text as input and not produce a sequence of Mel-Kapstel frames, but instead produce a sequence of these encoder states.
Correct.
So how do you train this TTS system? What do you do with the training data?
We first have a parallel data, and we first train the ASR system and the TTS system. But before TTS system train, we first train the ASR model, and then we have an encoder decoder, right? And then using this encoder to process the parallel speech feature to get the pair data of text and output of the encoder feature, right? Now we have this parallel data, and instead of predicting the Mel-Kapstel sum, we predict the encoder feature. So it is highly depending on the initial ASR model.
Okay.
Is it clear for you?
Yeah, what I'm thinking is that when you have different utterances of the same text by different people, you get a lot of speaker variability, but then you're hoping that your encoder states, once you go a few layers up in the whatever your stack of LSTMs or grooves or whatever you have, at that point you're hoping that speaker information has been removed.
That is our intention, exactly our intention.
But
that's why, yes.
I'm wondering whether how you initialize this recurrent layer might still retain or miss speaker information.
Yeah, there's some. So it's not perfect, but it's for now kind of what we are doing is in addition to do that, computational efficiency is also another reason. So that's why I kind of doing. But the data, we not finished all the experiment. We also try to input kind of using the speaker characteristic for the TTS system. So be patient. And the interesting result is that actually in the text data we have seen several kind of how to say the layer word that is not appeared in the parallel data, which is actually in general very difficult for ASR, end-to-end ASR to predict. But it can easily, not easily, but we can recover to predict such kind of layer word. Again, not appeared in the parallel data, but appeared in the text-only data, which is a quite interesting phenomenon. It actually had a long discussion with Google people, and they are pointing out this is quite difficult problem, and this is one solution. And of course, they're using the text-only data with a language model. We will have different the aspect of the boosting the decoder layer. So with this kind of a combination, we got the further improvement. So
this is the Libri speech?
It's exactly. This is the Libri speech data. So I want to just move to the other topic, which is the multi-speaker TTS and the others. But it's getting more, how to say, preliminary due to the time of the workshop time. But we still have a lot of kind of interesting ideas, and the results are ongoing. So one the topic is, of course, as I mentioned, we should also consider speaker characteristics in the TTS or even data augmentation. And this actually we asked the help of the colleague here and getting the X vector model pre-trained, and using this embedding vector fusing to our TTS system. And then we actually get the multi-speaker TTS. And there are several audio example. Again, if I have more time, I will play, but I will skip now. But I want to emphasize that we also, to some extent, get the multi-speaker TTS. Then another project is, of course, our target is multilingual. So why not multilingual multi-speaker TTS? That is mainly done by the Minson. And this is also a quite preliminary part, but I want to express that one. And this is again, if we have more data for the language, the various language, we can make use of that especially for the, how do I say, the acoustic part of the TTS system, similar to the Martin's presentation in the ASR part, we have some kind of language independent part and language dependent part. So multilingual, the multi-speaker TTS may help to improve the other performance of the individual low resource link, the single the language, the multi-speaker system. In addition, we may also realize the data augmentation based on these approaches. So this first result is actually monolingual system trained with TTS bubble data. Only 60 hours. It is not easy to get the text-to-speech. Actually, this is the attention plot. And we didn't see the good attention. We should have some monotonic attention, but it is not. But using a multilingual TTS system, it's hard to say, but it's getting some attention pattern. So that's not, still 20 epoch. We may need more epoch. But it's a kind of a clue that multilingual multi-speaker system may do some more the TTS system. So I just passed this one to the Leo about the other topic in the TTS.
Okay, I'm Rie Aihara from Mitsubishi Electric in Japan. So this is joint work with Tomoki, Shinji, Yu, and Takaaki, and Johnson. So, as Shinji explained, Taktron to estimate log mel domain spectrum. This is non-linear. So, what if we can estimate linear domain? Our TTS system will be more flexible. For example, we can consider the noise. As you know, many training data, noisy data is more. We have a lot of amount of noisy data. Clean data is to get clean data is so expensive. So in this linear domain TTS, we want to consider about the noise. Because Marl and Mitsubishi Electric has been devoted a long time to speech enhancement, so our experiment can devoted to combine speech enhancement and TTS. So this architecture is our proposing architecture. So conventional Taktron 2 only estimate log mel domain, but we first estimate linear spectrogram and also noise factor. We can, because it is linear domain, so we can add them and estimate log noisy spectrum, and we can calculate the loss function between target mel log spectrum. This is noise even. So this is kind of like a spectrum subtraction. So I have many options of loss functions. For example, our listener one is just to calculate mean square error between mel domain, but we can move to log linear domain, so we can add some noise factor. Also, we have another option. We can estimate linear spectrum, and we calculate the mel, and of course we can calculate loss function in the mel spectrum domain. So that is just my first trial. So I just first start training on the just estimating linear spectrum and calculate loss function in linear domain. And this is loss learning curve for this one. So this now we have 25 epochs, and loss is getting lower. And the next, my first trial is we just omitted the noise estimation part, and we estimate magnitude spectrum and calculate loss function in mel domain. And this one is also undergoing, and we have this learning curve. So maybe I can show you some good results in next week. Now, and also we are exploring the other cost function for estimating complex spectrum. We can estimate if we can do that. We can avoid the using vocoder, so that will be more effective. So that's all from my TTS team. Thank you.
Okay, good morning. So I'm going to talk about text-based data augmentation for end-to-end ASR as well. So this is going to be sort of parallel with the TTS, except we have another handicap. We're not going to use a TTS. So, so expect to see like much higher CERs. So the idea is quite straightforward. So we have an existing encoder-decoder model that we can train. And in this setting, we're assuming that one of the languages are our primary target. So in this case, say Tagalog. We're not actually giving it waveforms, but it was a pretty icon. So that's the main task. We're going to, one option is to just augment this data with other language pairs if you have access to them. And in this scenario that we're talking about, the other languages are going to be what we're calling auxiliary tasks. So it's not just to build a general purpose multilingual system, it's more like we want a good Tagalog system. How do we improve that? Maybe we can throw in other languages. So these are the auxiliary tasks. So the focus of this presentation or our project was to investigate how we can improve how we can improve a target primary task if we have only text-based auxiliary tasks. So the approach we're going to use is quite straightforward. It's sort of inspired by a back translation from the MT community. So suppose we get access to a large text corpus in the language that we're interested in. We get this text corpus, we apply a grapheme to phoneme, and this is something you've seen earlier in the talk. So you apply grapheme to phoneme and you get basically pairs of character sequences and phoneme sequences. And now we're going to try and use this pair of data as the augmenting data. And the way we do that is by basically extending the existing architecture of the encoder-decoder network with an extra encoder. We call this the augmenting encoder or the auxiliary encoder. And training is pretty straightforward. We're going to take one batch of data from our main task and do forward and back prop. And then we're going to take another batch from the auxiliary task, in which case it goes through this augmenting encoder, which accepts categorical phoneme sequences input. And we're going to do the same thing, and then we're going to basically just sample batches from both these tasks and train the network. Alternatively, what we also can do is, instead of feeding this in parallel, instead of feeding the two encoders in parallel to the attention, we can ask the augmenting encoder to come up with some representation that will be fed to the original encoder itself. So this is a little bit more aggressive style of augmentation because the MMDA basically influences the decoder and attention, and it's sort of saying, I know whatever my encoder does is not going to be very speech-like, so maybe I should just give it to the attention, and then maybe it'll help the language model implicitly in the decoder. But PSDA is going to try and affect the entire network, and potentially help the entire network as well. And also interestingly, like if PSDA works, we were wondering if we're implicitly learning a text-to-speech system. So if that edge that's going from the augmenting encoder to the original encoder looks more like speech, arguably the overall system is going to perform well. And so the numbers are as follows. So VoxForge Italian is like our pet data set. We used it a lot. It seems like it was small enough that you could run experiments quickly and sort of indicative of what you can expect in other data sets. So both PSDA and MMDA are like much better than the baseline, which is just an end-to-end encoder-decoder framework. And it's hard to pick a clear winner, but definitely PSDA is doing something useful, similar to MMDA. We also ran these experiments on Babel languages, so these CERs are much higher. We just used 10 hours of data in this scenario, as reflected by the baseline. So some of them are just very high, so it's hard to really make too much conclusions from something like 80 CER. But the trend is that both MMDA and PSDA can always beat out the baseline end-to-end system. And also, our original comparison was with multilingual training, and we find that if we use multilingual training, so we did this for Tagalog, so we added 10 hours of Bengali and Turkish, and we get sort of in the ballpark number. So there's like a trend, like since the PSDA is affecting more of the network, we feel like it's getting closer to actual multilingual training-based numbers, and the others are much higher. So So initially we thought that if PSD is helping, we're basically building a text-to-speech system while we're training an ASR. So we actually dug into our model and tried to see what the features that the augmenting encoder supplies look like. And they don't really look anything like speech. So what we see at the bottom is, so the above is basically the spectrogram from an utterance. We took the text associated with that exact utterance, and we applied G2P and got the phoneme sequence, and gave that phoneme sequence as input to the augmenting encoder. So this is after the training was done. And we basically tried to see what is on that arc. And I mean, we spent a lot of time staring at this, and some of us thought, yeah, this is definitely a vowel here. There's like a lot of energy here, and yeah. So we like if you stare at this long enough, you start seeing things that you want to see. Basically, you can't say there's anything there, but it still helps. So one of the things that we're interested in doing in the future is to actually try and get better and better at the augmenting encoder. So the architecture for this box here is one LSTM layer. So we're really not doing anything too fancy. So maybe if we start getting more parameters for the augmenting encoder, we could make it be more speech-like. Or when we have multilingual TTS systems training, which is sort of happening in parallel, we can actually just replace this entire module with the text-to-speech system. So while we were doing the PSD experiments, wait, do I have time to?
Well, you have to hurry up.
All right, okay, I'll hurry. So while we were doing the PSD experiments, we sort of asked ourselves, why is it helping? We're basically giving sequence of phonemes and then just saying, pretend this is speech and see if you can make use of it, and it sort of does, at least for the low resource settings that we're working with. And so our intuition was that if you're like really bad or like really far from your final destination, maybe anybody who gives you a general direction of where you want to go, so this person from New York wants to go to San Francisco, and if someone tells you the directions to LA, it's probably not that bad until you probably get to like Colorado or something, right? So the intuition here is that there's this notion of helpfulness of the auxiliary task and like how good the model is. And maybe as your model gets better, you can rely on the auxiliary task less. And if you are really bad, then any help is good help. And so we were wondering if it's possible if we say, okay, I'm going to try and get this curve a little bit higher by sort of being a little bit more discriminative about when I use the auxiliary task. And so we basically try to come up with an optimizer that's sort of aware of whether the updates are helpful or not when the updates are coming from this auxiliary task. And so the optimizer just says, I need some kind of scoring method to score every update. Theta I prime is like a potential update. If my potential update scores better than my current state, I'm going to take it, otherwise I'm going to reject it. And this score function is sort of, we're going to peek at the dev data and say, am I in a better place or not? So yeah, so this was option one that we tried. And we also thought of a softer version of this. So if you probably recognize that this is like added delta, and this entire expression here controls for the per feature learning rate. And so we said, instead of rejecting an entire update, which seems like a very drastic measure, we're going to reject updates to the learning rate instead. So we're going to always take a step, regardless of whether the score function says it's a good or bad step. But we'll be sort of a little careful and say, when we're updating our learning rate, we're going to pay attention to whether the step was good or bad. We have a cute name for this, we think. So it's added delta plus peeking at the dev, so it's data delta. And again, we did this on Voxforge Italian, but unfortunately, so we sort of expect this. So undo step is a little aggressive, but we were hoping that this beats this, but it sort of matches it, but doesn't quite beat it. So we still want to play with this idea some more and see if it helps. One of the motivations for this was when we were training PSD, we had like a lot of these hyperparameters to train or to test, like how much did you sample from the main data and from the augmenting data and so on. And we were hoping that this optimizer would sort of avoid having to go through those kind of hyperparameter tuning. But unfortunately, we're not there yet. So we did some analysis. We wanted to ask ourselves, how many batches does the augmenting data get rejected? So how often does it help according to the dev set? And how often does it not help? So our hope is to see something like this, right? Where we say, as the model gets better, it'll accept less gradients from the augmenting data. But we find that it's pretty much constant. Like it seems to always accept around 40% of the batches. And also we wanted to check if the gradients from the augmenting batches, if we compute the similarity between the gradients from the augmenting batch and the gradients from the main batch, we were again hoping to see something like, as you train the model better, the gradients diverge, and maybe you can then be selective about which gradients you apply. So this is our hope. And then again, you see something like this. So most of the gradient similarity. So we don't exactly know what's happening here. So we're comparing really large vectors. So it's quite possible that you get a cosine similarity that's mostly orthogonal because you're in such a high dimensional space. The only thing that seems to change considerably is these two blue lines, which are basically the gradients from the attention parameters. So attention seems to change within the first few epochs when we do PSDA. But all of the other parameters, so the red lines are the encoder parameters. So we're just basically taking like some matrix in the encoder and plotting the gradient for that. And the green ones are from the decoder. So there's no real trend to see here, and it definitely doesn't look like this. So there's still some investigation that needs to be done. This probably explains why just simply rejecting a batch, rejecting a step is not a very good idea. But this morning, when we're running experiments, and they kind of every time they come, we have to like figure out what's the story behind these new numbers now. So we ran the PSDA undo learning rate, and it seems to kind of sort of help Turkish and Swahili, but not Tagalog and Dokpesin. So it's still, so I wouldn't say that this data-aware optimizer is something that we should stop looking into. There's probably some hope left still. That's all for me.
So I know we're a bit late, but we will manage. So this is on the domain of paired data, and it's about cycle consistency. It's joint work between me, Takaaki, Sanjeev, and Jonathan. And basically, the idea here is to exploit cycle consistency to work with unpaired data. Today's cycle consistency is about you have two transformations that are one inverse of the other, and you build a model in which you just go from one to the other and come back, right? And by doing this, you can measure inconsistencies in the original domain, right? So you don't need to have all the data. You can have unpaired data. You can have only speech, for example, and go from speech to text, which you actually don't have, and go back from text to speech and measure the difference, right? And that's an idea that has been used in other disciplines, has worked very good, and we wanted to work with it here to see if we could work in the unpaired data scenario. We have some low resource and we only have speech or text. Let's see if it works, right? So there was some prior work in this direction. Mostly it was about either sampling or doing some sort of partial model. And what we wanted to do here is to create a real end-to-end differentiable system that would combine two complete text-to-speech and speech-to-text systems, right? As you have heard, SPNet has this advantage of having both a transcription system and a synthesis system that you can combine. So this is basically it. We would have SPNet, the original speech-to-text model, and we would have Tacotron implemented within SPNet as the text-to-speech model, right? And what we want to do is basically build the model out of those two. It's like a gigantic monster that basically integrates both and has in the middle this text transcription stage. So that sounds like a cool idea, but there's a couple of problems there. First of all, if you go from speech to text and from text to speech, that text doesn't contain a lot of information of the speech, right? So you have your speaker characteristics, your accent, your mood, whatever, that goes away, right? That's not in the text. So in order to be able to close the loop, you also need to have this additional pathway from speech there. to the speech synthesis, right? That's in this case we use expectors, but you just need some unstructured flow of information that gathers speaker characteristics. Once you have that, then you can measure this consistency there on the right side between the original speech and the reconstructed speech, and then have a measure of error. With that error, you can do backpropagation. Now, when you do backpropagation, you have that discrete stage in the middle, right? You were producing unknown texts. So in principle, it's not end-to-end differentiable, and that's what we wanted to tackle. We had both these problems. First, not end-to-end differentiable. Second, we need to reconstruct the entire speech. So the idea that we did was relatively straightforward. We basically used some of related work trying to approximate expectations for over the space of sentences. And what we did is we use SPNet to generate sentences. We generate a number of, we sample a number of candidates, and then we approximate the expectation by computing tachotron on those sentences and measuring the loss. That is, how consistent the original speech is with the speech that tachotron produces. It's a relatively straightforward approach that approximates this marginalization, this summing over all possible sentences that are unknown, right? I don't have that text. So I don't have the text, so I just need to produce some hypotheses, weight them, and backpropagate. So that's the main idea, and that's what we implemented. It sounds nice, but of course, if you just put a very big sequence-to-sequence model with a very big sequence-to-sequence model, you join them, and then you have to sample from one and use the other one to evaluate. That is a gigantic monster, right? So it has 3 types of different features, including the speech features for the ESR, the speech features for TTS, and then the speech features to maintain, to keep the paralinguistic information, right? That speaker characteristic. So we have to do a number of things. One of the things that we need to do is memory would be too big, so we end up, let's say, unparallelizing the batch update, meaning that you basically do part of the batch update with one SQL call, and then you have a for loop over different parts of the batch, right? And this allows us to be able to have reasonable memory sizes while having various samples. The problem there is that now it gets much lower. So in general, what happened is that this first approach is too slow, and it's in general it's hard to do things with it because you need a long time to see the results, right? Also, the idea of using X vectors as a way to keep speaker information, it's a bit limited. These are pre-trained X vectors. We would like to have some sort of direct connection from speech to the synthesis, right, for the speech text. So while we were doing this, we were also exploring in parallel 2 alternatives that kind of solve these problems. They're not exactly the original idea, but they also use cycle consistency. One idea that is also exploited in Tomoki's work and ended up being part, at least the part is used for one of the SLT submissions, is the idea of, okay, instead of doing text to speech to text or speech to text to speech, I'm going to just focus on the encoder of the speech to text system, right? And what I'm going to do is I'm going to run my train system, produce a lot of intermediate states, and instead of training the synthesis system to synthesize speech, I'm going to synthesize the encoder states, right? That's a relatively simple idea. Now, instead of targeting speech, I target encoder states, so I don't need to pull the speaker information through another pathway, because that contains, to some extent, that contains some speaker information, although, as Sanjeev indicated, with normalized, right? So once you do that, you still have the discrete bottleneck, so you still need to marginalize over sentences, but now you don't have to do the full synthesis of the speech, so it's much faster, and that allows us to run a bit more experiments. And the second idea that we tried is it's also a cycle consistency idea that is similar to what other teams have been testing here, which is, okay, so instead of focusing on doing text-to-speech and speech-to-text, both models have an encoder and a decoder, so I'm going to build all possible combinations of encoders and decoders. If I have speech and text, I can use one, or the synthesis and the ESR. If I only have speech or I only have text, I just build the corresponding text-to-text or speech-to-speech, and I train everything, right? And this approach was also quite faster. It doesn't have need for marginalization within the sentence space, and it's also a neat idea, right? So actually, those three models are running as we speak. Because they're relatively slow, we didn't get too much results. Validation shows that in general the models are improving. At least the last two that I presented, they're improving. They're showing results. Here I'm showing some examples. The one that worked best was this last one. This idea of just building all the combinations of encoders and decoders. And this one can leverage both text and speech, and we got some positive results there. Although this is again very preliminary. There's a lot of jumps to do. In general, I would say we did these three possible alternatives. They all exploit cycle consistency, so they all exploit this idea of unpaired data through cycle consistency. We do have initial results because basically playing with sequence-to-sequence models coupled takes a lot of time, a lot of computing time, plus the overhead of learning the tools. So we have settled a good ground for future work. We have initial results, and I think this direction is promising and will continue. At this point, it's obvious that if we want to keep the original idea of merging ASR and TTS, we need to somehow short-circuit the speech information in a more elaborate way that's not text vectors. Kyun Cho recommended, instead of full tuning of the systems, just tuning of some of the subset of parameters, which makes a lot of sense and would speed up things. And also the idea of combining encoders and decoders seems to be working best of the three, so we probably also will go farther in that direction. And that's basically it.
So I'm going to present some ideas of how can we use a generative model to train end-to-end speech recognition with incomplete data. I wasn't working 100% of this during the workshop, so I don't have the results, I just present some theoretical models. So the motivation for this work is that current end-to-end ASR is a discriminated model, so we need transcript audio to train it. But in many languages, we don't have data enough to train it. So we would like to take advantage of unpaired data. For audio-only data or text-only data. That is much easier to collect. We can download the audio from YouTube or text from Wikipedia. For example, in traditional ESR, this is kind of easier because we can, on the one side, we can use transcribed data to train acoustic model, we can use text data to train a language model, and we can compose both models and apply Viterbi algorithm. Our proposal to attack this problem is to use a probabilistic generative model of the generation of text and speech. And in this model, we can consider speech and text as hidden or observed variables depending on the data that we have. Implementation is in progress. So as a reminder, I'm going to remember the ASR end-to-end ASR model. So this kind of system contains an encoder. The encoder has to compute phonetic discriminant features that we could and then the decoder has to predict the test characters. And in the decoder we have some state variables. That state variables depend on the previous value of the state and the previous value of the character. And we use the state to compare the state with the age variables, and then we get some kind of alignment between speech frames and characters. That was what we call attention. And we use the attention to summarize the age variables into a context vector that will give us some information on what is the next character to predict. And then using the state and the context vector, we predict the character. So now we are going to take this model and we are going to try to build a generative model that is able to do the same. So this is not neural network, this is a Bayesian network, and the Bayesian network shows how to generate data showing us the dependencies between the different variables in the model. So we have in the upper part of the Bayesian network, we have the speech-related variables. On the one hand, we have the speech features that can be considered hidden or observed. If we only have test data, they will be hidden. If we have audio data and tests, we will be observed. We have this auxiliary variable R that will tell us when to stop generating speech. This can be also hidden or observed. And we will have the H variables. These are similar to the ones that we have in the typical system. And these variables will have phonetic information. These variables will be always hidden. And finally, we will have the set variables that should contain a intraphone variability. For example, the speaker variability, the properties of the mechanical properties of the vocal tract, etc. And in the lower part of the figure, we have the variables related to the test generation process. We will have the characters that will be hidden or observed, depending on the case. We have the states, the same states as we have in the traditional ASR end-to-end system. And we have the attention context that, for simplicity, we consider this a deterministic variable. So this model is completely defined by the joint likelihood of all the hidden and observed variables. The joint likelihood is decomposed in several conditional distributions. The conditional distribution for the characters is categorical distribution, and the rest of conditional distributions are Gaussian distributions, where the parameters of the Gaussians are given by a neural network given the parents of the variable. For example, if we want to get the likelihood for the speech frames, we will take the H and the Z variable, and we will put it into neural network, and that will give us the mean and variance of the speech frames, and then we can sample from that distribution. So to sample from this model, we will use ancestral sampling. So first we will sample a value for the first H variable. Then we take this H variable, we plug into the corresponding neural networks, get the corresponding distributions, and we can sample the next value for H, the value for R, and the value for Z. Again, we put Z and H inside neural network, get the distribution of the speech frames, and when we can sample the speech frame, and so on and so on and so on. And then once we have all the H variables, we can start generating tests. And first we sample some value for the state. We combine the state and the H variables to get the context vector, and then we sample characters, and so on. So in generative model, we have the generation phase, and also we have the inference phase. In the inference phase, what we want is to get posterior distribution for all the hidden variables in the model. I'm not going to enter in details because it will be very long. Yes, I will show an example. This will be this formula will show how the formula for the posterior distribution of the hidden variable in the case that where X and Y are observed. So each of these factors. So for each hidden variable, we have a different factor. Each factor, we assume that is a Gaussian distribution, and again, the mean and variance of those Gaussian distributions are given by neural networks. So for example, if I want to compute the posterior distribution for H, we see here, we could prove that the posterior distribution for H depends on all the previous H, all the future H, and all the Ys. So we will put these variables inside the neural network, we will get mean and variance for H, and then we can sample a value for H, and we can plug it here. We can plug here H and H, and then we can posterior distribution for Z, and then we can sample Z. So how we train the network? So we train the network maximizing a lower bound on the marginal likelihood on all the observed variables. So the evidence lower bound, to compute it, we need to evaluate some expectations, as the likelihoods that we have in those expectations are given by neural networks. We cannot evaluate those expectations in closed form. So we will use an approximation called stochastic gradient variational base that basically consists of using samplings. We sample the hidden variables from the posterior distributions to evaluate those expectations, and we use a parameterization tree to be able to propagate gradients through all the computational graph. Here I have an example of, so for each condition, the elbow is a little bit different depending on if it's a y arc observer or hidden. So for this case, it will be x and y will be observed. And this elbow will have several terms. So the first term will be related to our capacity to recover the speech frames. We could call this a text-to-speech loss. The second term will be related to the capacity of getting transcription. We will call that the ASR loss. And then the rest of terms are scale divergence that acts as a regularizer, where they try to make prior and posteriors close between them. So currently we are implementing a simplified version of this. So currently we are implementing a simplified version of the model where some of these hidden variables are assumed deterministic. And we plan to do some experiments and we will have some good results to implement the full model. Then we can experiment changing the relations between variables, adding some more hidden variables. And as this is a generative model, we can improve it using things like generative adversarial network or cyclogram objectives. So that's it.
Sorry, we almost use all the time for presentation. Yeah, actually, no one keeps time for presentation. Okay, so.
Try it, that's good.
Okay, so I just wrap up the presentation. So yeah, after this workshop, also we need to continue some research, and the main thing is to combine our proposed techniques and evaluate them using all 7 evaluation languages, and also we further investigate incomplete data training methods using multilingual data, and also we try to merge the developed things into ESPNet, and also we plan to publish some papers in major conferences. So yeah, anyway, I believe that we will be able to speak any language to a single deep network. So yeah, we are almost there. So, and finally, I'd like to thank everybody working on this project, and also some many people discussed about this project. So thank you very much.
I know we've run a little late, but if there are any general questions for the team, we could take them now. So the floor is open for a few questions.
Do you want to offer the YouTube viewers as well to ask questions?
Can they ask questions? Can they?
Yeah, there is a chat.
Okay, so those who are watching us live online, if you have any questions, what is the mechanism?
There is a chat window.
There's a chat window. Okay. Are there any questions, Jaime? From the from the.
So how long will it take you guys to end to beat the hybrid system? What's your expectation, guys? This is like open question. How confident are you guys? 1 year?
Yeah.
I mean, for interpretation, it was like, well, it will take, it took like 9 months. So you never know.
Yeah, if you give me the $10,000 of data, I can do it. Yeah. But for just to speak, we usually fight $100 or $1,000, and then we need more technique. But that's the kind of status, so it will be.
Were sequence models supposed to be making this nice and elegant? We're adding paths and multiple. This is just a hack to make it work on, or a hack to make it work on small amounts of data, and it will go away on large amounts.
Yeah, I think so. Actually, lot of techniques here, we actually developed for the kind of small amount of data. But some of the actually experiments showing that that improvement is getting smaller if we have a large amount of data, right? Which means that this kind of the development technology is important. But if we have more data, we may simplify the model. So that is a kind of a current status of overall kind of development.
Any other questions? So I guess one question I had for you guys is that you were motivating this early on by saying that you're basically trying to solve the speech problem for multiple languages. Have you noticed any trends in everything you've seen so far? Are some languages easier to get to than others, or what insights do you have at the end of the workshop? Are some languages easier to get to than others? Does it matter what related languages you have in which you have labeled data? And Martin's result, I suppose, was that the best thing you can do multilingually is to train these feature extractors which are multilingual. But I would say we knew that already before this workshop. What did you learn in terms of the multilingual models? Or anyone in the team? Yes.
So for example, my case, interesting finding was that I sometimes told it before. But anyway, for the sequence-to-sequence model, the length, character length is quite important. It makes the inference difficult. It makes the training very difficult in terms of the training time. But then, actually, Japanese, Chinese, these are ideogram language and very short. And then we found that sequence-to-sequence working very well. So these kind of difficulties are quite depending on the language and the writing system. Now, maybe BP or other techniques can kind of leverage, average these kind of difficulties. But sequence to sequence has some kind of dependency in the language, and that is a kind of interesting finding for us. And Martin may also have some other finding for that.
So, Shinji,
Yes.
follow-up question is that in the presentation there is a comparison with the sub-word unit and character unit. Why not just use the word unit? Because I thought that you already use library speech with almost 1,000 of our data, and the word unit, if you use word unit, it's short, and it's easy for you to predict.
Yes, this is a great question and suggestion. For our current problem, actually the amount of data is very small. And the word model is kind of difficult. But already you guys, Microsoft or other researchers, having a great success if we have a large amount of data. So I think this is definitely one way. And but character is a kind of between, right? So we kind of still investigating, especially when we have a multilingual data, the amount of data is quite unbalanced. So that's a kind of the current status, but it is a great suggestion, yeah.
So there are a couple of questions from the web, and I don't have my glasses, so Linda, can you just read them?
Okay. So the first question is from Myanmar, and the question is, for marking, how do the numbers compare to the bubble end-to-end numbers? And if you have any insights on that.
So just come up here.
Yes. Yeah, you mean like what the rates? Probably.
Probably.
Yeah, there are still, of course, worse, because the results what we have are mostly like phoneme recognizable character recognizable output. But what guys showed with the RNLMs, you can get pretty nice gain. But yes, of course, they are still behind about like 6%.
And that's the trick. If you speak directly through to RNN-LM, it means that you guys are not closing the whole loop, right?
Yes, but
That's
RNN-LM
not
is
like-
still character-based, right? So it still have no notion about the words.
Oh, you're saying you still don't have a word level model, is that what you're
Yes,
saying?
yes,
Okay.
exactly. So it's the reason why we estimate every single characters. It's pretty difficult to get it, but especially on low amount of data. You probably need to play with the decoder like Takaaki is doing.
Correct. I have one more question from Minma, which might also be question from Bhuvana, if I interpret the text correctly.
Okay.
And the question is for Shinji. When using TTS for augmenting with the text data, how does this compare to synthesizing all of the data first and then training the end-to-end model?
But still, if we train the older model, that is of course better. That we have actually oracle number in the slide, and I don't have I don't fully remember, but oracle number is like in the experiment like 5% for the CR, and our data augmentation is like 10% ish. So that we still have some kind of big gap of the data augmentation part, and if we have parallel data. So this gap is difficult to kind of fill up, but the TTS model is, if defined, we may lead to more about such kind of oracle result. Yeah.
Okay. One last question before we call it a day, or call it an morning rather. I think, all right. Yes, Thomas.
So I think a lot of techniques use the kind of using hierarchical models, which I assume are very powerful if you have low amount of data set, a small amount of data. Which of the techniques do you think will be still useful? Because I think hierarchical models might be actually long-term very beneficial if they reflect something that actually is true. That actually helps also with large data sets. Do you have any idea what kind of hierarchical structure might be useful on the long run?
We investigate several the hierarchical model, right? And one thing I still believe it is very important is like the several work is they try to make more hierarchical with the language model part and the sequence to sequence part with some kind of the code or feedback fusion or whatever. That is still, even we have tons of data, still we need to have make use of the text only data. I think this hierarchical system should be still important if we have 10,000 or 100,000 hours of data. And the others, I don't have an answer yet, but some of them should be very benefit in terms of if we have more data, we can use more complex system. But in terms of how to say intuition, I don't have an answer on that.
On that note, let's call the morning's proceedings to an end. So let's thank all the speakers again. For our online viewers, we'll go offline now and come back on just before